Hello and welcome everybody. Today in calculus we will be starting a new chapter and we will be putting away derivatives for the time being and start talking about the area under the curve. Now if it seems like it is a wide stretch because we're all of a sudden switching gear, they are related to each other. So you're going to find out how by the end of this chapter then. Okay, so here we go. In this first section, section 5.1, we're going to be talking about something called the Riemann sum. Okay, so section 5.1, Riemann sum, also known as the area under the curve. So the idea here is that given a function, I would like to estimate what is the area under the curve within a certain boundary for x using something that's called the left-hand rule, right-hand rule, middle rectangles, and also trapezoids. So we'll discuss what those are in just a little bit. So here is an example question. Here we want to see that what I would like to do is I want to find the area of the area under the curve for the curve y is equal to x squared from 0 to 4. This notation is basically the representation of that. So the way we write it or the way we read it is that it's the integral from 0 to 4 of x squared dx, which basically means find the area under the curve for x squared from 0 to 4 for x. So right here I can kind of write out the meaning, but that's the idea behind it. That's the notation anyways. Now, needless to say, we can't really easily find it because you can see that the upper bound, the height, is not going to be something that's consistent. We can't just go ahead and say base times height because it's not a rectangle. So we need to kind of devise a way to estimate it. And the way we're going to do that is first by creating something called the left-hand rule or the left-hand side rectangles. So here's what that means. So you can see in this picture over here, what I'm doing is from the area between 0 to 4, one easy thing I can do is create 4 rectangles and use those as an estimate as the area under the curve. So what I'm going to first say is let n be the number of partitions in terms of rectangles that we are using. In this case, n is going to be equal to 4. And the height that we're going to be referring to is the left-hand side. So here, for example, if you take a look at the picture of my curve, you'll notice that we have 1 right here, and then we have 2 right here, we have 3 right here, and 4 right here. Notice that the height of the rectangle is referring to the left-hand side of the ends of the interval each time. So that's what I mean by the left-hand rule. So going back to my picture over here, then that's going to be my estimation. Now, what I'm going to do is find the area of each one of those rectangles using base times height. So that's what each part represents. So the first rectangle on the very far left, you'll notice that the base is 1 multiplied by the height, which is f of 0, which turns out to be 0. So that part is kind of like almost irrelevant. But the next part, that's where it gets a little bit more interesting. Then the base is going to be equal to 1. And the height is referring to when x is equal to 1. And that's going to be 1 then. So because 1 squared, because since I'm plugging it into the equation, that's where that 1 comes from. The next height of the rectangle is going to be 1 multiplied by f of 2. So that's going to be this rectangle that's over here. So that's going to be 1 times 4. And finally, for the last one, it's going to be base times height. So it's going to be 1 times f of 3. So that's going to be 1 times 9. So there are my 4 rectangles. And if I add them all up, that will give me an idea, a rough idea as to what the area under the curve is. So in this case, we can say that it's going to be equal to 14 because that's the sum of all the numbers. And since all of these rectangles are underneath the curve, then this is going to be an underestimate. And this is the only way we know that it's the only way we know it's an underestimate because we drew out what the curve actually looks like. It doesn't necessarily mean that every time we use the left-hand rule, it'll be an underestimate. All right, now let's go ahead and say, hey, let's go ahead and make maybe more partitions because the more partitions we make, the more accurate it is. But then the problem is the size of the base is going to get smaller, and that's where it gets a little bit more complex. So in this case, you can see I'm going to go ahead and let n, the number of partition, is equal to 8, and we're still going to use the left-hand side rule. So the estimate for the area under the curve is, once again, always going to be base times height. And now there are going to be 8 partitions, as you can see, where the base of each one, the length is going to be 0.5. So it's going to be 0.5, then 1, then 1.5, and then 2, then 2.5, and then 3, and then 3.5, and then 4. The height each time is still referring to the left-hand side of the intervals. So nothing has changed except for the number of partitions and also the size of the base. But now by having more of these rectangles, then that way we can see that this is going to be a more accurate estimate, but unfortunately more work. So here it is. So 1/2 times f of 0 plus 1/2 times f of 0.5 plus 1/2 times f of 0.1, and so on and so on and so on, all the way to the last partition, which is 1/2, which is the base once again, times f of 3.5, because that's the height. So in this case, when we add them all up numerically, and by the way, f of x is still going to be my function f of x over here, right here. So then the total in this case is going to be 17.5, which is definitely a lot better than the previous one. This is still an underestimate though, because if you notice, the partitions are always going to be under the curve in this case, right? So now what I want to do is I want to think about how this works out, in the later future sense, because this is, this method is great and all, but it gets kind of, it gets kind of like troublesome, because by that I mean, well, if I want to be as accurate as possible, I need to create as many rectangles as possible. So that means that I want to have ideally like infinite number of partitions. But the problem there is, well, then that means you're going to have to do a lot of work. So the question is there a way for us to set it up so then that way maybe we can like throw it into a computer program to be able to solve for it, or maybe related to something that allows us to solve for this without having to actually draw 1,000 partitions to make it as accurate as possible. So here, what I want to do is I'm going to go ahead and write what I have in terms of the area in a format that allows us to see maybe a pattern. So if you notice over here on the bottom, you have the top right here. You'll notice that each one of these, they're multiplied by 1/2, which is the base. So that's the consistent part, right? So the base is going to be 1/2. Now, in terms of where all of these 1/2 is coming from, well, that's where this part comes in. You'll notice it's because it's 4 minus 0, which is the size of the base of the area under the curve that I want. Remember, the area under the curve is from 0 to 4. That's why it's 4 minus 0. And then divided by 8 because I want 8 partitions. And that's where the 1/2 is actually coming from. The rest of the part, f of 0, f of 0.5, f of 1, f of 2, f of 1.5, and so on, so on, so on, those are going to be the sum of all of the corresponding heights according to the left-hand side. And what I did was I wrote that as a summation notation that's on the left. So here, from I is equal to 0 all the way to 7, because that counts as 8 total partitions, from 0, 1, 2, 3, 4, 5, 6, 7. And then we have f of x of I, which tells me that I'm supposed to find out what is the height according to how far I move each time to the right-hand side. So that's just kind of like a general idea as to what's happening. Well, that is so far from the left-hand side. Now let's go ahead and say, hey, what happens if I use the right-hand side? So using the same idea, what I'm going to do now is I'm going to go ahead and say, let's look at n is equal to 8, because, that seems to be a pretty accurate area estimate of the area under the curve so far. But I'm going to go ahead and use the right-hand rule this side, or the right-hand side. And what that means is, once again, if I kind of like, blow into the picture of these rectangles, you'll notice that the height that I'm referring to for each one is according to the right-hand side of the end of the intervals. So from here to here, you can see that I'm using the right-hand height. From here to here, I'm using the right-hand height, and so on and so on and so on. And hence, that's why it's called the right-hand side. Now, if we were to write it as a summation of the base times height, right here, then according to the previous example, then it's going to be 1/2, which is the base of every single one of those partitions, multiplied by the first height is 0.5. Next one is going to be 1. Next one is going to be 1.5, and so on, all the way to the end, which is going to be f of 4. So it's still the same thing, but all I did was just write it in factor form. So if I add up all those numbers, again, using the same method, then you'll notice that the answer comes out to be a 25.5. In this case, and according to my picture, this is going to be an overestimate, because notice that every single one of those partitions are going to be overlapping with the curve. So that's going to give me a better idea as to what the upper bound is. So over here, you'll notice that I wrote it in a formation. I wrote it in a summation. So in that way, we can kind of see a pattern in the future also once again. 4 minus 0 divided by 8, so that's your base, multiplied by the summation of all the heights. And this time, you'll notice the difference is that I start with I is equal to 1 and go to I is equal to 8 instead of I is equal to 0 all the way to I is equal to 7. That indicates the right-hand side instead of the left-hand side. Whereas the function part, still the same thing, okay? All right. Now, if you're wondering, okay, well, is there something more accurate than the left-hand rule or the right-hand rule? The answer is yeah. We can definitely make it a little bit better. What if we use something called the midpoint rule? So what that means is we're going to use the height as the middle of the interval for each one of these. So that's what the midpoint rule actually stands for. So let's start with something simple first, okay? So let's go ahead and look at n is equal to 4 using the midpoint rule. So once again, in our picture over here, you can see there are my partitions. And the height each time, you're referring to the middle of the interval. So for example, over here, this is going to be 1, this is 2, this is 3, this is 4. So the middle right here, the height that I'm referring to is 0.5. And then for this one right here, the height that I'm referring to, or the x value that I'm referring to is 1.5. And then for this one is 2.5. And then for this one is going to be 3.5. So those are going to be my x values that corresponds to the height for each one of these. Okay, so then that's what I'm going to be plugging into my equation for the midpoint rule right here. So here is going to be 1 times f of 0.5, and then 1 times f of 1.5, and then 1 times f of 2.5, and then finally plus 1 times f of 3.5, which gives me 21 then. This right here, we don't know if it's an overestimate or it's an underestimate, but definitely for sure that it's going to be more accurate, because if you notice that for each one of these partitions, right, you'll notice the part that is overlapping right here is going to be the same as the part that is not counted for over here. It's almost like identical to each other. It's not exactly equal to each other. But, you know, I think that idea of having that 21 right there, that's pretty close to what we're actually looking for. Okay, it's definitely better than like the 17 or the 25 that we came up with before. And finally, well, after the left-hand rule, the right-hand rule, the midpoint rule, there's one last rule, which is called the trapezoid rules. And this one is definitely going to be a lot more accurate. And so what that means is, instead of making partitions that are rectangles base times height, we're going to look at them as rectangles. Sorry, not rectangles, but rather trapezoids. So over here, it's a little bit hard to see, but maybe I can kind of draw this a little bit better using a different color. So here, for example, you can see that this part, that is going to be a trapezoid right here. Then for the next part, I can look at this right here, the next partition, as another trapezoid. Okay, so let me just kind of like, you know, draw this in. So that's a trapezoid right there. The previous one, that's a trapezoid right here. The first one, well, technically that's a triangle because the height on the left-hand side of the trapezoid is 0. But all of these guys, now you can kind of see that, yeah, they are all going to be the shape of the trapezoid. So in terms of like, how do we solve for it? Well, we just need to go back to geometry and learn how to solve for the area of a trapezoid. The area of a trapezoid is always going to be 1/2 times base 1 plus base 2 times the height, where the height is really referring to the length of the partition. So that's where the 1 comes in this case. Whereas base 1 and base 2, well, that's where the height of the function comes in. So the area of the first trapezoid is 1/2 times f of 0 plus f of 1 times 1. Then the second one is 1/2 times f of 1 plus f of 2 times 1, and so on and so on and so on. And then finally, we're going to go ahead and add them all up. So the sum of all of these trapezoids will give us then the estimate of to what the area under the curve is, which in this case is going to be 22. If you're wondering which one is more accurate, is it midpoint rule or is it the trapezoid rule? It actually varies. But for the most part, trapezoid rule is always accurate, I think, within like say 0.1 of the error percentage. Sorry, it's like accurate within like I think like a certain percentage. I can't remember that off the top of my head because I learned this like about 10 years ago. But trapezoidal rule is definitely probably the most accurate out of all of them. Maybe somewhere tied between like midpoint rule. Okay. All right, so that is going to be the idea behind it, okay? But then now the question is, okay, well, Mr. Chan, what if somebody gave me a chart value than rather an equation? Because, you know, you notice that I gave you like a nice equation like y is equal to x squared, and we don't always have that. In reality, what happens is some people will not give you an equation, but rather they'll give you a chart. So the question then is, well, how do you find the area under the curve if I give you a chart like the one below, like a tabular chart? That's what they call it. Well, here is an example of the problem. With the chart that's given over here, what I want to do is estimate what is the area under the curve from 5 to 14 of f of x dx using the left-hand sum with 5 subintervals. Okay, so here in this chart, I want to know what is the area under the curve from 5 all the way to 14. Well, keep in mind, we're using the left-hand rule, and the idea is still the same thing. We're going to go ahead and make partitions then. So the first partition that I'm going to see is the first piece from 5 to 6. That right there, the base is equal to 1. And the height is, since going to be referring to the left-hand rule, is going to be equal to 7. So that's where I got this part right here, 1 multiplied by 7, because 1 is the difference between 5 and 6, and 7 is the left-hand height between the interval of 5 and 6. The next part, same thing. This time around, I'm going to go ahead and look at the next interval, which is from 6 to 2 pi. Okay, so then the base is going to be 2 pi minus 6, and then multiplied by the height that's on the left-hand side, which is the 4. Then we'll do the same for the next one over here. From 2 pi to 10, I'm going to find a difference for the base. So that's going to be 10 minus 2 pi, multiplied by e, which is the height that, again, is on the left-hand side. And so on and so on and so on all the way to the end. And if you notice, if I look at all the partitions, that's 1, that's 2, that's 3, that's 4, and that's 5. And hence, that's where we got the 5 subintervals. So now we just go ahead and add them all up, and that's where we got the 16.822. Now, can we kind of like, make up values in between? The answer is no, because you don't know what the function is. So I can't go ahead and say, oh, between 5 and 6, since it goes from 7 to 4, then maybe the average of it, which is like 5.5, is going to be the value you get when x is equal to 5. Well, what kind of function is it? We don't know. It could actually be 1. So basically what I'm saying is don't fabricate any information that you don't know about. Just basically use what's known. Okay. All right. So let's try next one right here. Just same idea. This time I'm saying, hey, let's go ahead and estimate the area under the curve from 2 to 14 using the middle Riemann sum with the 3 subintervals. Just to make it a little bit easier, I just redrew the chart down here just so that way we can see how that works. All right, so from 2 to 14, that's basically from the far left end to the far right end. And what I want to use is 3 subintervals. Now, if you're not seeing where the 3 subintervals in terms of what we have in terms of data, well, here's what it looks like then. Here, from 2 to 6, that is going to be 1 interval, right? And then from 6 to 10, that's going to be another interval. And then afterwards, from 10 to 14, that's another interval. Basically, each one of these interval has to have a quote-unquote midpoint, even though it's not exactly the middle of the interval. But that's basically the idea behind the midpoint rule right here, right? You're using what's in between. So for each one of these, let's go ahead and solve for it then. So for the first subinterval, from 2 to 6, the base is going to be 4 because that's the difference, 6 minus 2. Multiplied by f of 5, which is the height of that interval. So that's where the 7 is going to come in. The next piece, I am now going to look at from 6 to 10 over here, right? The difference in the two values, that's the base, which is going to be 4, multiplied by f of 2 pi, which is the height, which in this case is e. And finally, for the last one over here, the distance from 10 to 14, that is going to be 4. And by the way, this is all coincident that the base is always going to be 4. It could be something different next time. And the height in this case is going to be the middle term, which is going to be f of 11, which is 0. Find all of that, add them up together, and that right there will then be our estimate of the Riemann sum using 3 subintervals with the middle, or the midpoint rule. Okay? And finally, for the last one, okay, well, the trapezoidal rule. But I think by now you get the idea as to what's going to happen. Just basically using what is available for us. Estimate what is the area under the curve from 10 to 14 of f of x dx using 2 trapezoids. So then that means we're basically using this part over here, and we're just going to go ahead and build trapezoids according to those values. So t of the trapezoid of 10 to 11 plus the trapezoid from 11 to 14, and once again for each one, 1/2 base times height. 1/2 times base 1 plus base 2 times height, and then plus 1/2 times base 1 plus base 2 times height, and then find the total area for the sum of the two, and that's going to be our answer then.